Welcome to G Fun Facts Online. In the immense quiet expanse between the stars, countless wanderers drift. For most of history, they were just a ghost in our equations, a theoretical possibility. But now, we've seen them. Tearing through our own solar system, these visitors from other star systems have given us a glimpse into the galaxy's hidden nursery. They are interstellar objects, or ISOs. Comets and asteroids forged around alien suns and then violently ejected into the void. And their brief passage is more than just a celestial light show. It suggests these cosmic vagabonds play a central role in one of the universe's most epic stories, the birth of planets. The story of how planets form has been a grand puzzle for scientists. For decades, our best models have been troubled by nagging paradoxes. How do microscopic dust grains, swirling in a disk around a baby star, grow into the massive cores of gas giants like Jupiter? How do they overcome the physical barriers that should, by all rights, send them spiraling into their parent star? The answer, it now seems, might not come from within these young solar systems at all. It might come hurtling in from the darkness, in the form of ready-made planetary seeds that jumpstart the entire world-building process. This is the story of a hidden network of creation, a galactic ecosystem where the death and disruption of one solar system can provide the building blocks for the next. Our understanding of this hidden world was purely theoretical until 2017. In October of that year, a telescope in Hawaii spotted something moving so fast and on such a strange path that it could only have come from beyond our solar system. It was named One-Eye, Oumuamua, a Hawaiian term meaning, quote, a messenger from afar arriving first. And it was deeply weird. Oumuamua was nothing like the familiar comets or asteroids from our own cosmic neighborhood. Its brightness varied so wildly that astronomers concluded it must have a bizarre shape, maybe a highly elongated cigar or an extremely flat pancake, perhaps 10 times as long as it was wide. Its reddish color suggested a surface that had been bombarded by cosmic rays for millions of years. Most puzzling of all, as it sped away from the sun, it accelerated slightly, pushed by some mysterious force. Normally, a comet accelerates because the sun's heat vaporizes its ice, creating a jet of gas. But Oumuamua had no visible tail or fuzzy halo of gas, known as a coma. This lack of a coma ignited a firestorm of debate. Some scientists proposed it was a nitrogen iceberg, a fragment chipped off a Pluto-like planet from another system whose invisible nitrogen gas provided the push. Others suggested it was a fluffy, porous chunk of dust. One of the most provocative ideas, championed by Harvard astronomer Avi Loeb, was that its shape and acceleration were consistent with an artificial solar sail. While most of the scientific community leans toward a natural explanation, Oumuamua proved that interstellar objects could be far stranger than we ever imagined. Then, in August 2019, a second visitor arrived, discovered by amateur astronomer Gennady Borisov. 2I Borisov was, in many ways, Oumuamua's opposite. It looked and behaved like a classic comet, complete with a bright, beautiful coma and tail. This was a relief, confirming the long-held theory that ejected comets should be common, interstellar travelers. But Borisov had its own secrets. Its chemical composition was unlike almost any comet from our own solar system. It was extraordinarily rich in carbon monoxide, with levels up to 26 times higher than our local comets. Carbon monoxide only freezes at incredibly low temperatures, below -250 degrees Celsius. This suggested that 2I/Borisov must have formed in an extremely cold, distant part of its home solar system, perhaps around a dim red dwarf star, the most common type of star in the galaxy. The trio of known interstellar visitors was completed in July 2025 with the discovery of 3I/Atlas. Like Borisov, Atlas was clearly a comet, but with its own distinct personality. The James Webb Space Telescope showed it was rich in carbon dioxide ice, which also points to formation in a very cold place. It was also the fastest of the three, hurtling through space at a staggering 58 kilometers per second. Together, this trio paints a picture of a galaxy teeming with ejected planetary material. They are the leftovers from planet formation in other star systems, and their very existence is the foundation of a revolutionary new idea about how all planets, including our own, come to be. To understand why these visitors are so important, we first have to appreciate the huge problems in our traditional theories of planet formation. For decades, the leading model has been the core accretion theory. It's a bottom-up process. It starts with a young star surrounded by a rotating disk of gas and dust. In this disk, tiny dust grains stick together through static electricity, like dust bunnies under your bed. Over thousands of years, they form centimeter-sized pebbles. Then, through processes we still don't fully understand, these pebbles clump into kilometer-sized bodies called planetesimals. These are the first true planetary building blocks. These planetesimals then start colliding and merging, with the biggest ones growing fastest, eventually forming planet-sized embryos. In the inner, hot part of the solar system, you get rocky planets like Earth. In the cold outer regions, these embryos can grow massive enough to pull in huge amounts of gas, becoming gas giants like Jupiter. While this theory sounds neat, it has a killer problem known as the, quote, meter-size barrier. When those pebbles grow to be about a meter wide, they run into a serious headwind from the gas in the disk. This drag force is so strong that it causes these meter-sized boulders to lose energy and spiral into their parent star. And it happens catastrophically fast, in as little as 1,000 years. That's long before they have a chance to collide and grow into bigger, more stable planetesimals. It's like trying to build a sandcastle in a hurricane. Another major issue is the timescale problem. Those disks of gas and dust don't last forever. They are usually blown away by the star's radiation in just 3 to 10 million years. That sounds like a long time, but for the slow process of core accretion, it might not be long enough to build the 10 Earth mass core needed to form a gas giant like Jupiter. The construction site shuts down before the foundation is even finished. These paradoxes have opened the door for a radical new idea. What if planetary systems don't have to build everything from scratch? What if they get a little help from their interstellar neighbors? This brings us to the cosmic seeding hypothesis. The theory suggests that young protoplanetary disks can capture wandering interstellar objects, which then act as seeds for planet formation. This elegant idea solves the meter-size barrier in one clean stroke. Instead of struggling to grow from dust to kilometer-sized bodies, a young solar system can simply import them, fully formed, from interstellar space. These captured ISOs, being hundreds of meters to several kilometers in size, are big enough to be immune to the gas drag that dooms the smaller meter-sized rocks. They've already crossed that barrier in their home system. Once captured, they provide a gravitational anchor, a ready-made foundation that can immediately start sweeping up dust and pebbles from the disk, dramatically speeding up the entire planet-building process. But how do you catch a speeding bullet? An interstellar object is moving at tens of kilometers per second, on a path that should just whip it past the star and back into deep space. To be captured, it has to lose a lot of energy. The most efficient way this can happen is through gas-assisted capture. A young planetary disk isn't empty, it's a dense fog of gas. As an ISO plunges through this disk, it experiences powerful gas drag, like the friction you feel sticking your hand out of a moving car window. This friction can be strong enough to slow the ISO down, bleeding off its excess speed until it's trapped by the star's gravity, settling into a stable orbit. Simulations show this is surprisingly effective. A single disk could capture millions of 100-meter objects and hundreds of kilometer-sized ones over its lifetime. The planet seeding hypothesis doesn't just solve the meter-size barrier. It also directly tackles the timescale problem. By providing a head start with pre-made, kilometer-sized seeds, the process of building a giant planet's core is radically accelerated. A captured ISO can start growing right away, potentially reaching the critical size for pulling in gas well within the 3 to 10 million year lifespan of the disk. This idea is especially good at explaining how giant planets form around very massive stars. These stars are hotter, and their disks dissipate much faster, sometimes in as little as 2 million years, leaving almost no time for traditional core accretion. But these same massive stars are also more efficient at gravitationally capturing interstellar seeds, giving them the boost they need to form planets quickly. The implications of this theory are profound. It recasts our vision of the galaxy from a collection of isolated solar systems into a dynamic, interconnected ecosystem. Planet formation is a generational process. Old solar systems eject their leftover building blocks, which travel for millions of years before being captured by a new generation of stars to seed the growth of new worlds. No planetary system is an island. This galactic recycling program also has fascinating implications for the distribution of life, a concept known as lithopanspermia. If these interstellar seeds can carry the raw material for planets, could they also carry the building blocks of life? A rocky object like Oumuamua could potentially shield organic molecules in its interior from the harsh radiation of space, delivering them to a new, possibly habitable planet. The ongoing revolution in astronomy is about to put this theory to the test. The Vera C. Rubin Observatory in Chile is expected to start finding dozens, if not hundreds, of interstellar objects every single year. This will give us a huge statistical sample to understand their population, their composition, and how they truly influence the growth of new planets. Future missions could even be designed to intercept one of these objects and study it up close, giving us a direct sample of material from another solar system. The hidden world of interstellar objects is no longer entirely hidden. With each discovery, we are peering deeper into the cosmic web that connects star systems. These messengers, born in chaos and flung into the void, are not just relics. They are the seeds of future worlds, the silent architects of cosmic creation, and a fundamental, previously unknown, chapter in the story of how we all got here.